Welcome to ECEN 215 Principles of Electrical Engineering. Today's topic is the introduction to operational amplifiers. At this point in the course, we kind of take a shift where we have been doing a lot of circuit analysis and a lot of things like involving mathematics with phasors. Now we're going to start looking at some more practical aspect of devices and things that you're going to see in your career as an engineer. Um, so one of the first things we're going to look at is a device called an operational amplifier. So an operational amplifier is actually an integrated circuit. That is a device in which there are various transistors, which we'll be going over in a later lecture, resistors, sometimes integrated capacitors as well. And these devices are all placed onto a silicon wafer. And then those wafers are cut down into little devices called an integrated circuit or a chip by various processing steps, for instance, photolithography. These silicon devices are all integrated together and then packaged in an epoxy enclosure usually, and with all of the leads coming off of the IC being exposed for you to actually solder onto a printed circuit board. Now, these amplifiers originally were contrived for use in analog computers. And so where the name operational amplifier comes from is that these different circuits, these different integrated circuits would actually perform various functional tasks, various actual mathematical operations such as integration, differentiation, multiplication, division, subtraction, logarithms, so on and so forth. So it actually did perform truly mathematical operations, hence the name operational amplifier. This is kind of a picture of what a simple operational amplifier looks like. An 8-pin is known as a dual inline package IC, probably about half the size of a dime in size, a pretty small little chip. And nowadays they actually are even more, simplified and smaller than this. Some of them are about the size of probably not much bigger than the end of a mechanical pencil eraser. Probably somewhere in the neighborhood of like a millimeter or two in size. So an ideal op amp, again, this is when we say operational amplifier, the amplification part is what we're interested in. So what we have here is an ideal op amp, and the emphasis here is on the ideal part, because what do we mean by ideal? And we're going to kind of go over what some of those properties are. So an ideal op amp, the circuit symbol looks like this. We have this triangle here that represents the amplification part, where we take some sort of an input, and we have a non-inverting input and we have an inverting input. And we're going to take the net difference between the two, and we're just going to amplify it by some value, known as the amplification open loop value, AOL. So for instance, if AOL, this is not what it really is, but it's just for instance, if it was 5 volts per volt, then if V1 minus V2 was 1 volt, then the output voltage would be 5. If V1 minus V2 was 2 times AOL, VO, or the output voltage, would be equal to 10, so on and so forth. So this is the general circuit diagram here for what an ideal op amp is. Now, what is important to note is you notice there is no input voltages. It is ideal, meaning that it gets its power ideally just on its own, and it can supply whatever the maximum value is for a V out, and it will definitely produce an output voltage that's related to AOL times V1 minus V2. So now first let's define some definitions of an operational amplifier. First, there's the input common mode signal. This is the average of the input signals and is known as the common mode. And the idea is that this is basically if both of these are together, and it's just the average of V1 plus V2. So this is the common mode. So basically think of it, if I had two signals, both of them were centered at 0 volts, both, like say we're going to inject AC signals into the amplifier, then the common mode would be if both of them were centered around DC at 0 volts, then you would have 0 plus 0 divided by 2 would be 0 volts. So that's called the common mode signal. Now, in the end, you do not want any of the common mode to actually carry through. You're just looking at the difference between the two. Now, the differential signal is truly the difference between the two input voltages. Again, we have two input voltages, V1 and V2, and we're actually interested in strictly the difference between the two. Input impedance, as you've seen before when we've talked about resistance or impedance, this actually refers to what, if you will, the load is on V1 and or V2. And ideally, it would be infinite. There would be no load on the input value. It would be whatever voltage one is, you would, you read that voltage, if you will, but you would not apply a load on that voltage. So ideally, input impedance on an ideal op amp would be infinite. It would be infinite ohms. So it does not cause a load on the input signal. And the output impedance would, in theory, be 0 ohms. I would want to drive the output to exactly the voltage I'm setting and always maintain that voltage. So think of this in the terms of the Thevenin circuit that we've gone over multiple times in this class. So here we have a power supply that in theory would be, in the case of the output, it would be the output resistance. And so what we have here is we have our RT, and this would be our VT. So imagine, if you will, that VT really is equal to the open loop voltage times V1 minus V2. If RT is equal to 0, then you're guaranteed to get this value here. So ideally, you want this to be 0 ohms. Whereas here, think of it as this, where the input here, this is a VN1, say, and if the input resistance, say we have some sort of RT, and this is our circuit staring into our ideal operational amplifier, and it connects on these terminals here, right? So we have our two terminals. If there is a load resistor here, RL, if this is something other than infinity, it's going to pull a current and hits the voltage here. V1 is not going to be the voltage at this point, the VN, which is what we really want. We want V1 equal to VN, which requires RL to be infinity ohms for that to occur. And so that's why we want the input impedance to be equal to infinity. Bandwidth refers to the frequency range of the signals that the amplifier will handle without doing any distortion or signal loss. Now, as we have seen in our frequency response lecture, we have seen that different circuits respond differently at various frequencies. For instance, low pass filters, high pass filters, band pass filters, and the band reject filters. So ideally, you would have an operational amplifier that would handle all frequencies, everything from DC all the way to infinite hertz. So ideally, it would handle everything without any signal loss. So an ideal op amp, again, has an infinite input impedance, has an infinite gain for the differential input signal, has a 0 gain for the common mode input signal, has 0 output impedance, and it provides infinite bandwidth, meaning that it can take any signal on V1, V2, regardless of the frequency, and the output is going to be equal to infinity times V1 minus V2. So that is what is the ideal properties of an op amp. Now we're going to actually look at the circuit model for this. So now looking at the schematic symbol for this op amp, you will notice that we have our positive input here, and that's represented for V1. We have our negative input here, representing for V2. And our output is going to be V out is equal to AOL, which we determined a moment ago. AOL is equal to infinity volts per volt times, in this case, the positive input minus the negative input, or in this case, V1 minus V2. And of course, we have our output resistance, but for an output of an ideal resistance, or the ideal output resistance for an ideal op amp is equal to 0 ohms. So this is our ideal case. Now let's, instead of drawing this, so this is what we use currently for drawing our ideal op amp and the circuits that we're going to be looking at shortly. But what does this look like using symbols that we have used historically in this class in the past? So let's take a look at that. So we can replace everything with just our inputs being V1 and V2. Again, this is our positive input V1, our negative input V2. And so we have our input differential voltage, VID, which is V1 minus V2. So everything's kind of standard. Notice there is no any components tied to V1 and V2. It is just basically a node in space here because there is no resistance. There is no input resistance. Rn is equal to infinity ohms. So that's part of the ideal op amp model. So we're just needing the difference between these two voltages. So these could be connected anywhere else on the inside of another circuit. Then we have this element here. And of course, you may have recognized this for some of the homeworks and some of the things we've done up till now in class. This is a dependent source. This, in fact, is a dependent voltage source. And it is dependent upon another voltage, in this case, VID. So we have a voltage-dependent voltage source. And it, of course, uses AOL, which AOL, again, is equal to infinity volts per volt. And it's going to be multiplying that times VID. And, of course, again, if there was output and resistance, it would be here. And R out is, in this case, equal to 0 ohms. So now that we have our circuit model, let's now investigate if we use the circuit model in a configuration, because having what we call the open loop model of the circuit really doesn't do us any good, because any small difference here, I mean microvolts, nanovolts, is not going to matter. Anything is going to cause this thing to go to infinity. We're going to now use something called feedback, and we're going to create a new circuit using this circuit model and show different types of circuits we're going to build. So let's go ahead and investigate what that looks like. So this is the circuit that we're going to create. We're going to have an input voltage here coming into Rn. So this is just some sort of power supply of some kind. It could be a sinusoid source, something. And it's going to generate a signal Vn. And then we're going to connect our negative input here. So this V2 is our negative input, and V1, the positive input, we're just going to tie to ground. So notice we're just going to hook it straight up to our reference node here. So that AOL is V1 minus V2, and this is our output. And we have this resistor here, and this is called the feedback resistor. And so we're going to see what this circuit configuration does as we go. And of course, there's a node here that connects everything together. So let's go ahead and start doing some basic circuit analysis on this. So first thing we notice is we can start writing the equation immediately for V out. That one's pretty easy. V out is simply equal to AOL V1 minus V2. We know that immediately. So let's go ahead and write that out. So V out, AOL, V1 minus V2. What else do we know? When we look at this, we have V1, we have V2, and we have V out. When we know everything, the only thing we don't know is V2, because we know what V1 is. V1 is 0 volts. It's ground. So we can go ahead and put that down. Now, V2 is a node, and we know using Kirchhoff's current law, we can do an analysis on this node here. And one thing, of course, to note is that that we have current, going three possible ways. We have current that could be leaving this node, going this direction. We have current that can leave the node and go in this direction. And we have current that can go this direction. Now, let's look at that. So let's go ahead and write an equation for this, where we have I1, I2, and I3. And using Kirchhoff's current law, we know that V2, for the node V2, I1 plus I2 plus I3 must be equal to 0. Now, what can you tell me about I3? I3 is staring into an infinite resistor. There's no place for this current to go here. There is nowhere that this current can go. It is staring into infinity. It's just infinite resistance. So there is no current flowing in I3. So we can simplify this by simply going, that's gone, because I3 is ideally 0. So we can reduce this equation simply to I1 plus I2 is equal to 0. Now that we know that, we can actually write the formulas for I1 and I2. Because simply put, we have this node here, V2, and we just need to know the current going this direction, which is just simply V2 minus Vn over our Rn, and that gives us I1, and I2 here again is V2 minus V out over Rf. So let's go ahead and write those out. So now we pretty close to have almost everything we need. So we can start combining everything together and start to see if we can simplify this, this model. So let's go ahead and do that. So now we have V2 minus Vn Rn plus V2 minus V out over Rf. So we just basically wrote out our equation. I1 plus I2 is equal to 0. And again, we know that V out is equal to V1 minus V2. And since V1 is 0, it's just AOL times V2 with a negative sign in front of it. So we can go ahead and insert that into our equation. And we end up with V2 minus Vn over Rn, and then V2 plus V2 over times AOL divided by Rf is equal to 0. Move the constant over, which is just a Vn over Rn, so that we have the left side of the equation is everything in terms of V2, and then the right-hand side of the equation is the constant that we can pull out of this. And then we can factor out V2, and now we can simplify this a little bit further. Kind of repeating the formula here. So we have V2 is equal to Vn over Rn, because we now are just multiplying this Rn times this value here. So we do that, and just kind of simplify this through a little bit. And now we end up with V2 is equal to Vn 1 plus Rn over Rf plus Rn AOL Rf. So let's take a look at this formula here. Let's see if we can make some determination on V2. So this is what we have. I'm simplifying it a little bit further with using the actual value for AOL. We now have this infinity in here in the denominator. We have 1 plus Rn over Rf plus Rn over Rf times infinity. Which makes what? It makes this entire term here go to infinity. Well, now we have an infinity in the denominator. So what does that do? So that takes us Vn over infinity, which means this actually is 0, because anything divided by infinity immediately goes to 0. It's just the nature of the mathematics. So what does this mean? That means we've created a virtual short circuit, that V1 and V2 are tied together, that this power supply here, this dependent power source is doing everything. And given the circuit configuration, it is outputting enough voltage here to compensate to keep this node equal to this node, which just so happens in this case to be ground. So that's what's happening here. That is known as a virtual short circuit, and in this type of circuit configuration is sometimes known as a virtual ground. This type of circuit, if you go ahead and let's go ahead and finish the analysis now, because now we know what V2 is. So we should be able to finish our circuit analysis and actually determine what is the actual, what we call closed loop gain. What is the actual gain of the circuit? Not necessarily the gain of the actual operational amplifier, the open loop gain, but what is now the closed loop gain? So going back to the circuit that we had earlier, we have V2 minus Vn over Rn plus V2 minus V out over Rf. So we have this, but now V2 is equal to 0. And if that is equal to 0, then we simply end up with minus Vn over Rn plus minus Vout over Rf, which leads us to the open loop gain, or the closed loop gain, AV, as it's also known. This is the closed loop gain. The closed loop gain for this amplifier is minus RF over Rn. This is known as an inverting amplifier. That is what the circuit, and we're going to see this again in the following topic lecture regarding different operational amplifier circuits. So now let's talk about real op amps. So we've been looking at ideal op amps, and as we saw earlier, the ideal op amp did not have power supply connections. Well, of course, for a real op amp, and this is actually a real part number for an op amp, LM741 is one of the very first op amps that came out in the late 1960s. It's made by pretty much every silicon manufacturer there is. For instance, I'm going to show you the one from Texas Instruments here in a moment. And there really must be power supplies. Again, there is a non-inverting input. So that would be this input here. There is an, excuse me, I'm getting this backwards here. There is an inverting input, which is this. There is a non-inverting input right here. And there is an output. There is a power supply that's positive. And then there is the negative supply, pin 4. It's right here. Now there are two other pins, if you notice. There's a thing called an offset null, and this one here. And this is for nulling out the output. Normally, this is usually left open, but it is there for you to kind of set, to correct for any drift that the op amp really will have. Because there is sometimes, this isn't with this being a ground and this being ground, or both being equal. Like if you connect a wire here, just simply do this, where your common mode is the same, so your inputs are equal to the same. Sometimes this output here is not equal to 0. And so you would use the offset null pins to adjust for that. But in reality, that's usually not too much of a concern. We're talking usually millivolts. So if you have a real precision circuit, that was a concern. But in general, for basic instrumentation needs, it usually is not a problem. Most op amps, in fact, you can actually buy op amps right now in a small package where it literally is just focused on these pins here. So here's an actual data sheet of an op amp. So if you go on the Texas Instruments website and you type in LM741, you will actually find this data sheet, and they give you the typical application. As you can see here, this is known as a non-inverting circuit amplifier, and we will actually be talking about this in the simple circuits topic for operational amplifiers and how that works. So they give you a typical application. They tell you that various different things it can be used for, its features, etc. And of course the pin out of the package, which we were just looking at this package a moment ago, blown up. So you have that. And of course, one of the things you always got to pay attention to when you're looking at real devices, there are voltage limitations. So there are supply voltage limitations for this. For this particular model of op amp, the LM741A and 741, you're limited to plus or minus 22 volts. And with the C, you're limited to plus or minus 18 volts for the supply voltages. It can handle a power dissipation of up to 500 milliwatts. And so you got to pay attention to that. And the max differential voltage is limited to plus or minus 30 volts. So that is very important to pay attention to these. And of course, the input voltage in the end is limited to plus 15 or minus 15. So that's where you can get the plus or minus 30, but you cannot put anything more than 15 volts on a particular input pin. So again, when you're working with real devices, you really got to pay attention to these absolute maximum ratings. If you violate these ratings, the chip will actually smoke on you. There's a phrase in the electrical engineering world where we actually usually say, well, you're letting the magic out of the chip. Well, that's what happens if you over voltage an IC, you will let the magic out. And it kind of stinks. So you don't want to do that. There are operating temperatures to pay attention to as well, depending on the variety. This here is your more industrial range for a chip, and this is more of your commercial range, so on and so forth. Now, one thing I wanted to show you here, the interesting thing, and I'll blow it up here, is when it gets to, so you got like your input resistance. So we talked about that a moment. Ideal input resistance is in the megohms. So typically it's 2 megohms. It's not infinite, but it's really high. It does talk about your basically your common mode rejection ratio, which is really high here. But the really interesting thing is the open loop gain. So here it's called the large signal voltage gain. And here it's 200 volts per millivolt, which is in reality 200,000 volts per volt. So this is equal to AOL. It's not infinity, but it's pretty high. So in summary, what we've looked at in this particular topic is just a quick introduction to what an operational amplifier is. And then we talked about what ideal characteristics for an op amp, if we had an ideal op amp, what those characteristics are. And we also talked about in general, what the characteristics for any general operational amplifier is. For instance, the bandwidth, the common mode gain, the open loop gain, AOL. For instance, the op amp we were just looking at a moment ago was 200,000 volts per volt. You also have the input and output resistance. Ideally, it would be infinite for the input resistance. The one we were just looking at for the LM741 was 2 megohms, etc. And then, of course, we did a basic circuit analysis using an ideal op amp with AOL set to infinity. Technically, you could go back using that same arithmetic we just had a moment ago and put for AOL, you could put the 200,000 volts per volt in there. And you're going to see that approximately it works out the same. That AOL is so high that mathematically we end up still with that circuit configuration. We're still an inverting amplifier of minus RF over RN with a little bit of additional gain contributed by the AOL. And then we actually looked at what real op amps actually do and what they look like. So if you've got questions, please come to the Q&A session and we will go over that in more detail. Have a wonderful day.